Thank you very much. First of all, I would like to introduce myself. I was busy at the university for studying from 1987. Then I did my PhD at Aachen University and worked for 12 and a half years in the chip removing machine tool builders industry from 1997 to 2009, before I joined the Reutlingen University with the chair of machine tools controls and additive manufacturing. From my side, I'm busy with the process chains for a very long time now, for over 30 years. And by the way, I'm coming from the machine tools, so I know what is serious production. And coming to the additive manufacturing, I saw that the serious production is not still working up to now. There is something to do. We are reading about additive manufacturing as a pre-shaping method, and we are going to diversify these methods into primary shaping with liquid slurry, pasty-like, or with granular or powder here. But I put it beside because there are some different methods which can be used. In the machine tool area, there are several solutions how to produce parts like a gear housing or a motor engine block in big numbers of parts. For example, 1 million parts of the motor engine block, or same cycle time for the gearbox. And these solutions grew up over a long time that they get for a very good process, and that the quality of the parts is given by the rough part, the machining, the assembly, and the finished components and assemblies here afterwards. There are combined different technologies like chip removing technology, assembling, washing, honing, washing, leak test, quality assurance. This is state of the art in these parts and this technology. This is not given at the additive manufacturing up to now. There are some uncertainties which lead to the fact that the processes are done often manually. And here are the process chains of classical production. We have a primary shaping, then forming, particularly depends on the parts, machining, and then afterwards coating, change material properties, joining, and so on. Additive manufacturing substitutes not the complete process chain. In the beginning, some years ago, I had the feeling that additive manufacturing substitutes also. No, that's not the case, because the tolerances which can be yielded by the additive manufacturing process are not so good that the parts can used afterwards directly. So we have to do a reduced extent of machining, and also the coating, changing material properties, joining, depends on the material we are producing. This is mostly here for the metallic parts, this process change, but it's similar to the plastic parts. Let us take a look where we are busy with. There are several different additive manufacturing technologies. Here at the show we can see all of them, but we are only busy with the industrial used plastics production with the SLS, selective laser sintering process. This is a technology we have in our lab, and we can test it in our lab together with our employees and do all the technology. We are not working in the SLM. By the way, it would be nice to me to have something, but there we are working together with the suppliers in our region and get some parts if we need them. Here this share of the metal market share of the metal additive manufacturing, most of them is the SLM, and then some of the others. So the industrial use parts and plastics are often done by SLS or by stereolithography. It comes up and more that also the FDM is used, or the HP multi-jet fusion method is comparable to the SLS from the parts quality. But let us take a look what has to be considered producing parts. We did a nice project where we developed a Additive which includes a lot of design features which have to be considered analyzing additive manufacturing parts. There are combining functionalities. There are blanks and slots, threads, friction bearings, then bores with different diameters which can be produced here. Very small bores can't be produced, or they can be produced, but they can't be cleaned afterwards. This is one of the major fields I would like to present to you. And then there are some structures here, frame structures or honeycomb or something like that. Then ball connectors, joints, and so on. And these design features we integrate into the part, and also somewhat additional the fonts, for example, which are printed on the surfaces, some step patterns here with stairs effect, or combined function integration. Different kinds of edges which are produced. And so we found out that there are some questions have to be answered. That we can optimize the production concerning accuracy and quality. We can optimize concerning costs or the mechanical properties. It is very difficult to find out this production system which optimizes all three factors. And then the production took place, and we have to take care about the post-processing. And post-processing in the plastics process chain is mostly done at this time manually. There are some drum cleaners I would present afterwards. They can do automatically unpacking and cleaning out the outer geometry, but for the complete cleaning and quality assurance, it is not possible to have an automated process chain. And this is one of our goals. We would like to fill the gap between the additive manufacturing process and afterwards the surface finishing and the parts handling and logistics then. And we considered the existing unpacking technologies. There's the vibration sieve, for example. There is also the rotational drum or tray conveyor. We can see some examples here on the show. And also there is exhaust or blasting technologies. But how they are equipped with a powder cake and how the parts are handled after they have been cleaned, and how is it made sure that the parts are really cleaned, also internal structures. And this would be very interesting field of application to have a complete automated and very flexible technology. Another aspect is how the powder should used afterwards. State of the art in our machine, and this is one of the market leaders or one of the big players, you have to use 50% new powder and 50% old powder, recycled powder. But if you're considering that there are only a share of 5 to 22% of the build volume is used for the parts, then you put away 25 to 50% of the powder by disposal. And this is very expensive. And so there should be a process which can lead that the disposal powder, the share is reduced very much. This is another field where we would like to give an answer by using the powder in different qualities. That we did some tests already, how to decide which powder can be used and which powder is not usable. Here's some photographs of parts which are unpacked. They are not cleaned up to now. And the powder which is still adhering at the surfaces of these parts can't be used. The powder which is between the most can be used again. We tested it, how to go on cleaning the parts and identify them. We are going out from the situation that we have a build job where I integrated many different parts, very flexible, like a service supplier is producing for different customers. They would like to use the build volume in a very good way, that they have many parts inside and use the production capacity optimal, so that the costs will be reduced. And then you have to decide how to clean the parts and which parts can be cleaned, for example, automatically. And then we considered what is done to do that. We have the build process where the machine is running for several hours with defined technology. This is not part of our research work. Then the cooling process where the build volume is put out of the machine in a cooling device in an exchangeable container, but afterwards the unpacking and the fine cleaning. This is a field where something has to be done. The pre-processing showed us which parts can be cleaned up automatically, because they are not so sensitive, they do not have any surfaces, they have no drills or no blanks, slots and things like that, which can be broken or damaged, or beam structures which can be damaged by the automatically drum or conveyor belt process. Then we have surface finished parts or surface cleaned parts, but we have to machine or to clean them internal, for example. The holes, slots, the bores and things like that have to be cleaned. And there we developed some nice tools which can be used for doing that. Automatically hoses, automatically tubes which are put into the holes. And so we cleaned up the parts and found out that the unpacking, depowdering and also the quality assurance of the parts can be automatic. Then we have the parts which are produced in one build volume, where different parts have to be combined with the CAD models. They have to be identified to identify the different features on them, which have to be cleaned. The drills have to be, or the bores have to be found by the automatic robot-based cleaning process. And then we installed identification for each single part, which combine or compares the part from the camera with the CAD model, and then decides which elements have to be cleaned afterwards. And the quality assurance can be done with the same system after the complete cleaning has been done. Then the integrity or the intactness checking is done, so that there are no damages. And we developed a process where the parts are unpacked, depowdered, and the parts are completely cleaned with different types of tools, but not manually. And this is one of our goals where we are producing the tools, or where we develop the tools. We are not producing them, we only have it in our lab done by several times, and different kinds of parts, and different geometries, and different cycle times. So we also considered which technology can be used. The drum, for example, and the conveyor belt is good, but only for the outer geometry. Blasting, internal contours is done for open internal structures or geometries, but only limited because sensitive areas can be damaged by that. Then we did some ultrasonic basins tests, where we tested several different liquids in the ultrasonic, but neither the ultrasonic vibration nor the liquids can lead to a clean part and put the powder out of the bores. Another test we did was by vibration, here with piezo element or piston vibrators. Also this test was not successfully. But we did some very nice tests up to bores from a diameter from 3 millimeters, where we can use some hoses or some tubulars to get into straight and circulars or banded bores, where we cleaned them up and were very successful with it. And this technology was done with the identification of the different features, and also with an automatic drive of the tools, that they lead to a good geometry and a clean part afterwards. This is a complete process here, where we also would like to integrate a powder recycling cycle here in the future, where we decide which powder can be used again and which is not usable by a crossing, which is automatically choosing the direction, disposal or recycling by a quality sensor which is integrated. And then here the robot-based cleaning process. So we found out that our sample parts, where we integrate here different types of geometric contours and features inside. Here you can see the drill bores which are not straight. Also here some different radius, different depths of the bottom holes or the through holes, which are integrated in these parts. The important step in the beginning is to identify here the different parts. Here is one build volume with many different parts shown by these signs. They are separated here on a conveyor belt, identified, and then the robot takes them and put it to the tools. And therefore it is necessary to have a system with machine vision. We have a robot and a defined place where the workpieces are located. A limited situation is that the accuracy of the vision cameras, the robots, and the build process leads to an error amount of plus minus 3 to 4 tenths of a millimeters. This is sounds a lot, but it can't be reduced because the build process and the robot and the camera resolution don't allow us to make it more accurate. But usually it is enough to identify and to clean the parts. How we are going on to design some sample parts, we define which features should be produced. For example, flow optimized or contour adapted bores here, then frame and honeycomb structures to make it lightweight. And then I presented already some other pictures of it. We define which sizes and which dimensions should be investigated, and we print it on our machine. And then we developed at the end some technology. If the parts are not cleaned on the surface or not completely cleaned, where are the bores located? We have to locate it, and then we have one method with infrared heating where we use the feature that the powder which is in the bores has not the same thermal conductivity like the rest of the solid material, and wait for some time and see with the infrared and camera where the bores are located. This is still in a development, this technology, but it comes up. And so we are busy for now many years with this thing, and we believe that the industrial production of additive manufactured parts has to be increased and developed and fully automated. And this is our goal, which we would like to supply by our research work. Thank you very much, and I'm open for some questions.